Today in Applied Calculus, we're going to start our curve sketching unit. So that is using information about derivatives to give us information about original functions. Eventually, we are going to get to where we are identifying maxes and mins, and those apply to any field you can think of. Any field you can think of, there's something that you want to optimize, whether that means actually minimizing something or maximizing. That's our ultimate goal. We're actually going to start today with a little bit of a review. So we're going to review the meaning of a partition number and how to do a sign chart. So for a partition number, the partition number of a function is when that function either equals 0 or does not exist. The sign chart, this is a review all the way back from pre-calculus. We then again reviewed it along with our continuity section, and we're reviewing it again. Remember that you're going to find those partition numbers that we just mentioned, draw a number line, use the partition numbers as the dividers to create a table, and then test to the left and right of each of those partition numbers to check for sign changes. We have been doing that with the original function. We're now going to be doing that with the derivative function. So we're looking at an original function here. Now in the future, we'll be doing something a little more complicated than this, but right now I am just asking you to read right off this graph. And so you can see that on this graph, we've also marked some little tangent lines, some examples. Of course, you can draw a tangent line from any point, but we've drawn a couple example tangent lines. And so when I look at this first interval, from negative infinity to negative 1, you can see that this function is increasing. It is rising as you read left to right. There's a couple tangent lines that were sketched in to help you see, and you can see that those tangent lines all have positive slope. Well, remember, the slope of the tangent line is the derivative. So what we're seeing is that in order for this function to have this increasing shape, the derivative must have been positive. The slopes of tangent lines must have been positive, angled that way to make it rise when you read left to right. In this interval between negative 1 to 1, you can see that the function is decreasing. It is falling as you read left to right. You can also see on the tangent lines that are sketched in that their slopes are negative. And if you think about it, they would have to have that negative slope to then make the graph have that falling look as you read left to right. So the slopes of tangent lines are negative there. The derivative is the slope of the tangent line. So it turns out when the function is decreasing, the derivative is negative. And then for our last interval from 1 to infinity, you can see the function is increasing again, and that if you look at the tangent lines that are sketched in there, they all have positive slope. And the positive slopes of tangent lines means the derivative is positive, so when the derivative is positive, the function is increasing. And so that is summarized here, and will be one of two basic things that we're going to get in this section that we're going to use for the rest of this section and for the rest of the unit as a whole. So we need to know that any x's for which the derivative is positive, the original function will be increasing. Any x's for which the derivative is negative, the original function will be decreasing. You'll hear me say that plenty of times during this lecture. Also, we need to be able to use it the other direction, that if an original function is increasing, the derivative must have been positive to create that shape that it can increase. And when the original function is decreasing, the first derivative must have been negative. So the other main thing, those two facts together is one main thing that we need. The other is this idea of a critical value. Why do we care about critical values, which we'll use enough that I will abbreviate CV, critical value. Some books also call it a critical number. It means the same thing. They are possible maxes and mins. And I told you that our goal in the long run is to identify maxes and mins in real-world problems. So that's where we're heading. So just keep that in mind. A critical value is a possible max or min, so that means that if you're going to have a max or min, it's going to happen there, but not every critical value will end up being one. And what is it? Well, we're going to have to be careful here between a critical value and a partition number. So a critical value is a place in the domain of the original function where the first derivative either equals 0 or does not exist. So the key there is that the x value that we're referring to that makes the derivative either equal 0 or not exist has to be in the domain of the original function. A partition number of the derivative, so not of the original function but of the derivative, would be a place where the derivative equals 0 or does not exist. End of story. So what we're going to be talking about is that both of those start the same way. places where the derivative equals 0 or does not exist. So we're going to identify those partition numbers, and then only if that x value is also in the domain of the original function can we call it an actual critical value of the function. So we're going to look at that right now. It's really going to come into play when we look at rational functions, in other words, fractional functions, functions where you end up having asymptotes. Because if something is not a critical number, but it is a partition number, we're still going to want to put it on our table, that sign chart that we were reviewing, to test, because interesting things can still happen there or change there. But we can't actually call it a property of the function, a critical value of the function, if it was never in the domain of the function to begin with. So we'll work more on kind of telling that apart. But right now, you're going to have a few questions that ask you, tell me the partition numbers of the derivative and tell me the critical values of the function. So that's what we're going to practice right now. So these say find the partition numbers of the derivative and critical numbers of the original function. They start the same way. We're going to start by looking for partition numbers. Partition numbers are places where the derivative equals 0 or does not exist. That means that the first step for all these problems is going to be to take the derivative. So you can see here we have a fraction. It needs the quotient rule. So we have bottom times derivative of the top minus top times derivative of the bottom, all over bottom squared. Do some simplifying, and we get negative 24 over x minus 6 squared. Now, partition numbers are places where the derivative equals 0. Well, this will never equal 0. If there's no variable in the top, then you can't change x, vary x, to make this be 0. This top will always be negative 24. So I looked for them, but there aren't any. Places where the denominator equals 0 will cause the derivative to not exist. Well, that will happen when x equals 6. So right off the bat, the second that x equals 6 causes the derivative to not exist means that x equals 6 is a partition number of the derivative. However, because x equals 6 would cause a division by 0 problem in the original function, x equals 6 is not in the domain of the original function, and so we cannot call it a critical number. So x equals 6 is a partition number of the derivative, but it is not a critical number because it was not in the domain of the original. Now, stepping it back a level, getting a little bit simpler, here we have a polynomial function. Well, remember the domain is all real numbers, so we're not going to run into those issues. So we still take the derivative. We think, are there any places where this derivative does not exist? But without any division, there can't be division by 0, and without any roots, there can't be any roots of negative numbers, so there's no problems. So then we're just looking for places where that derivative equals 0. We factor and solve and see that that's x equals 2 and negative 2. So we have found partition numbers of the derivative. Then we check, is that in the domain of the original function? Yes, it is. So they are also critical numbers of the original function f. So x equals negative 2 and 2 are both partition numbers and critical numbers. In C, I want to show you that just because a derivative has a fraction in it doesn't mean you'll be in the same boat that we started here. Notice that this original function, 2 minus x, lives in the numerator. It would be to a positive 1/3 power. It's not until we take the derivative and use that power rule with our chain rule and get 1/3, leave the inside alone, subtract 1 from the power to get negative 2/3, then times the derivative of the inside, don't forget the negative 1, then that quantity goes to the denominator. So that quantity was not in the denominator in the original function. The original function actually has a domain of all real numbers because it is an odd root, not an even root. And so we look and say, okay, the derivative will never equal 0 because there's no variable in the top. It will always be negative 1. And the derivative would not exist when the bottom is 0. When you work through that, it'll be at x equals 2. So x equals 2 is definitely a partition number of the derivative because that is any place where the derivative equals 0 or does not exist. But then we have to check, can we call it a critical value? And up here, we weren't able to. But here, x equals 2 really is in the domain of the original function as well. It's okay to take a cubed root of 0, right? 2 minus 2 would give you 0. Cubed root of 0 is 0. That's allowed. So since x equals 2 is both a place where the derivative does not exist and is in the domain of the original function, then it is both a partition number of the derivative and a critical value. So you kind of see different cases where you can and cannot call a certain number both a partition number and a critical value. And then we'll revisit that more in a few sections when we're actually graphing rational functions. So the reason that we were looking at these critical values is because they are the locations of possible maxes and mins. But we need to talk about, what are these maxes and mins. So there are two different kinds of maxes and mins. One is an absolute max and min, which is absolutely the highest spot or lowest spot on the graph that you are provided. So you can see here it's a filled-in circle that ends the graph. It's not going on with an arrow up to infinity, and that is the highest thing on the whole graph. So what you're hearing me say is highest and lowest. That means that a max or a min is referring to a y value. We will use the x's to talk about when or where a maximum occurs, but the actual max or min value is how high or low you are, and so it's a y value. So these are absolute maxes and mins. Then we have something called a local or relative max or min, and these are going to be the ones we're looking for when we're dealing with critical values. So a critical value is a place where a derivative equals 0. That means you have a horizontal tangent line, and look what happens there. If you have a horizontal tangent line, it means you're at the bottom of the roller coaster, right? Or here, also, I have a horizontal tangent line, and it's because I came up the roller coaster and I'm sitting at the top about to go down there. The other place that we have critical values are places where the derivative does not exist. Well, remember, the three ways a function can be fail to be differentiable or have a derivative. One of them is a sharp turn in the graph. And so notice here, there's a sharp turn in the graph. The derivative does not exist there, and it turns out that that looks like the bottom of a valley, right? A minimum as well. So why is it called local or relative? Well, that's not the lowest thing on the whole graph, but in a little area around it, locally or relative to the things around it, it is the smallest. So anytime you have something that makes the bottom of a valley, that would be a local minimum, or the top of a hill will be a local or relative maximum. Now, this spot happens to be both an absolute minimum because it's the lowest on the whole graph, and a local or relative one because it creates that bottom of the valley shape. So we are primarily going to be working on local or relative maxes for the next few sections, and we will revisit absolute maxes and mins at the end of this unit, but we need to know the difference between them before we start hunting for them. So what we have is that fact that when the if my function is decreasing and I think about the tangent lines, their slopes are negative, which means the derivative is negative there. And then if my function is increasing and I think about tangent lines, their slopes are positive, so the derivative is positive there. So we're actually going to use the signs of the derivative to tell us the increasing and decreasing of the original function to help us locate these maxes and mins. So critical values are the only possible places we might have these maxes and mins. So we're going to check at this C as a critical value and see if it turns out to be a max or min. So it's a possible max or min. We have to confirm that it is by checking the signs and using that relationship we discussed. So if your derivative goes from negative to positive, that means your function went from decreasing to increasing, and it makes the shape of a minimum. If your function goes from, your derivative goes from being positive to being negative, then your function goes from increasing to decreasing, and it gives you the shape of a maximum. Now, if you're at this critical value and you test to the left and right of it, and the sign does not change, like in these last two examples, you will not have a max nor a min. So here's a place where the derivative was negative and then negative again on the other side of the critical value. That means your function decreased. Maybe it leveled off a little bit, but it did not make the shape of a minimum, and then it decreased some more. So that does not end up being a max or a min. And here's the other case where maybe we were increasing and then increasing, and we have neither a max nor a min. So not every critical value will end up being a max or a min. That's what we're going to be testing for. If it looks like one of these first two cases, then yes, we'll have a max or a min. If it looks like one of these last two, then it will not be the location of one. So we're going to put this all together in what a problem will really look like. So this is what a problem will look like, although I won't give you the table, but we're kind of warming up. So the function, it gives you a function and says to find all local or relative extrema. Extrema is the plural word to include maxes or mins. And so I'm looking for the local maxes and mins. Well, remember, maxes and mins, if they're going to occur at critical values. How do I find a critical value? What we need to start going off in your head the second you hear critical value is first derivative equal to 0 or does not exist. Now we also know we have to check the domain of the original function, but first derivative equals 0 or not exist. So I need to take the derivative. Now I don't want you to forget to check. There are no places this derivative would not exist, but you at least need to think about it because there will be problems where there are. But there's no division, there's no roots, so there's no places where that will happen. So then I'm left just looking for the places where the derivative equals 0, and it's going to be a factoring problem. So the 3x squared can only be 3x and x. The 3 in the back can only be 3 and 1, and then I have to check the negatives. And then remember, the whole rest of this problem is going to rely on these values being correct. Take the time now to double check and FOIL it back out so that the whole rest of the problem's not wrong. All right, so we got 3x squared minus 9x plus 1x does give me a negative 8x for my inners. And my outers combined, and then the negative 3 and 1 were chosen to make sure that I get a negative 3 back there. So I'm setting each factor equal to 0 to find my critical values. Okay, so we've done sign charts before. This one's going to be a different version of a sign chart, but the principle is going to be the same. So I'm going to take my critical values, and I'm going to put them in order on a number line. Now the scale doesn't really matter. Like I can have the same amount of space in my little table between 1 and 5 as I do between 7 and 30, but the order does. And so I need to put the negative 1/3 to the left of the 3. And so if you were drawing this yourself, which I will model for you in a second, you would draw your number line, and then instead of drawing a tick mark to represent this number, you'll do a whole line down to be then the column divider as well. So what we've done is created a number line where each column represents an interval. And so that's what these columns are representing, are these intervals. And as with sign charts before, what we're going to do is pick a test value within this interval, strictly within. Notice it's an open parenthesis, so I cannot pick negative 1/3. What would happen if I did pick negative 1/3? Well, I'm going to plug it into the derivative, and I'm going to get 0. Why? Because that's how I found it. I found it by setting the derivative equal to 0. So it's not going to be helpful at all. So I want to pick a number that's strictly inside of this, and you can pick any number you want, but whenever you can pick nice ones, that's nice. So whenever negative 1 or 1 or 0 is an option, I usually go for them. And then in that last one, you might pick 4, you might pick 5, you might pick 10, whatever seems like a nice number for you. Remember that we could all pick different numbers, but the idea is these dividers, negative 1/3 and 3, the critical values are the only possible places that our signs could change. And so any number in this interval will give you the same result in terms of sign. And so whatever's happening at one spot is happening for that whole interval. That's the idea. And so then this sign chart is specifically called a first derivative table. So keep that in mind because you are checking the sign of the first derivative. And we're going to use the factored version because it makes checking signs really easy. If you don't use the factored version, you have to be careful because you won't be able to use these sign shortcuts that we use, because it is not true that a positive plus a negative always has the same result, right? It depends on the absolute values of the numbers. But it is true that a positive times a negative is always negative, no matter what, and that's the kind of tricks we're going to be using. So what we're going to do is plug our test values into our factored form. All right, so I plug negative 1 into each of them, and I think about the sign. In my first factor, I don't actually care what the number is, I just care what the sign is. And I lied, that would be a negative. So I'd have negative 3 plus 1, so negative 2, which is negative, and here I'd have negative 4, but all I care about is that it's negative, and a negative times a negative is positive. So why were we doing that? Well, because it's a very quick way to see that the derivative is positive, and when the derivative is positive, this is that big thing we starred on the second page, the function is increasing. All right, short for increasing. So that's the point of this first derivative table. We check signs of the derivative to apply that fact that we've now learned to tell us what the original function is doing. Then I would plug in 0. If I plug 0 into the first factor, I get positive. If I plug 0 into the second factor, I get negative 3, so negative. And a positive times a negative is a negative. When the derivative is negative, the function is decreasing. And then over there in the last column, when our x is 4, when I plug in, I'll get positive, positive. When the derivative is positive, the function is increasing. So then we say, well, what shape did this make? So is this what the function actually looks like? No, but it gives us an idea of what's going on. And so we can see that if my function was increasing and then decreased, then I get the shape of a max. If my function was decreasing and then increased, then I have the shape of a min. Now what we have to be careful about is that these x values of -1/3 and 3 are when or where these maxes and mins occur, but I don't actually know how high or low this goes. This is just a quick visual representation to help me see there is indeed a max there or a min there. But to find the actual y values, this goes all the way back to the beginning. This is y equals, right? G of x is just function notation for it, but it's y equals. We always go back to our original function to find the y's. So you can see I've done that for you. I need to plug my two critical values, if they ended up being maxes or mins, into the original function, back up to that cubic function. So you have to be really careful. We are past the days where I can ask you, what do you do next? And you just say plug in. Because there's multiple functions floating around. There's an original function floating around and a derivative function floating around. And we plug into both of them for different things, just like when you wrote equations of tangent lines, right? So for this first derivative table, I'm plugging into the first derivative. But when I need to know y values, I'm plugging into the original. So you need to be really clear, both with yourself and communicating to me on paper and writing, what you're plugging into. So I'm plugging into the original, and you can see that when x is -1/3, y is -13/27, that was our relative or local max. And when x was 3, y was -19, and that is our relative or local min. So you could say that the local min is -19 and it occurs at or when x equals 3, and that the local max is -13/27 and it occurs at or when x equals -1/3. So sometimes your homework will have you enter an ordered pair, and sometimes it'll have it kind of in that written out form where it's really stressing to you that an actual max or a min is a y value and that the x tells us when or where it happens. So then we're going to look at one from scratch where the table isn't already drawn for you. Okay, so here is part of what a problem will actually look like exactly on your test. So we're going to keep using this format. There will be no surprises. There never are, really. But there will be no surprises on your test. Now, the rest of the question isn't showing because we haven't learned it yet. We have to learn we have to learn that in the next section that we're about to get to in order to do the rest of the problem. But I'm going to be building up, and you'll know exactly what you're doing when you get to the test. So I have it broken down into parts, and that might look daunting, but it's actually a gift because it gives you cues as to what to do while you go. So critical value, you just learned it, but as you practice, that has to say in your head right away, first derivative equal to 0 or does not exist. Now, there's the whole domain thing, but first derivative equal to 0 does not exist, at least is a good starting place. So as I mentioned, the first step to pretty much every problem in this whole unit is going to be to take the derivative. So we take the derivative. This is just a nice power rule. There are no places where the derivative does not exist, but I need to think about it. And so I find the places where the derivative equals 0. And that requires factoring. And then I'm going to set each factor equal to 0 to get my critical values. So I've got x equals 0 and x equals 3/2 as my critical values. So the next thing, I can go ahead and write that down. So part A is accomplished by taking the derivative and setting it equal to 0 or seeing when the derivative does not exist. Parts B, C, D, and E can all be answered with a first derivative table. So you would draw a number line, put your critical values in order, but instead of tick marks, go ahead and draw lines all the way down. Okay, and remember each column represents an interval of x's. We're going to pick test values. It is called the first derivative table. So we're going to determine the sign of the first derivative and use it to tell us the increasing or decreasing of the original function. So that's how you would set it up when a table is not provided for you. I am expecting, even if you show your tables a little bit differently than I show my tables, I am expecting a table with work and not just answers to these. Again, you are not allowed to use a graphing calculator, so I don't see much way around how you would do this without showing work anyway, but you definitely need to be showing your work. So once we have our intervals set up, remember the idea is that these are critical values, these are possible maxes and mins, and I'm checking the signs of the derivative to confirm the increasing, decreasing the function to see if they actually are or not. And so I need to pick values. So make sure they really are in the intervals, but -1, 1, and 2 work. And then I'm plugging into the factored form. Now notice that the first factor here has squaring, and so no matter what you plug into it, you will get a positive. So the first factor of all these will be positive, but then I need to decide the sign of the second factor. So when I plug -1 in, I get 3 minus -2 times -1, so 3 plus 2, which is positive. And a positive times a positive is positive. When the derivative is positive, the function is increasing. Next, I would plug 1 in. 3 minus 2 would still be positive. And the positive times the positive is positive, and when the derivative is positive, the function is increasing. And so something that you should be noticing is, even though I do tend to give you nice problems, do not start thinking that just because this is a positive, you can just blindly alternate, oh, it's going to be positive, negative, positive, like it was in the last problem, because it won't always happen. All right, and then if I plug 2 in, I get 3 minus 4, so it'd give me a negative result. Positive times a negative is a negative, and when the derivative is negative, the function is decreasing. All right, so if I look at this, here I do not have a sign change in the derivative, and it's going to be increasing and then increasing again. So this is neither a max nor a min, whereas over there I have increasing then decreasing, and I get the shape of a max. So what we see is that we don't have a minimum. Don't leave this blank, and that implies to me you're not sure. Tell me you know there are none. You've done the calculus work to prove it. There are none. So write none or NA or something like that. But for max, I'm going to need the ordered pair. I'm going to need the y that goes with it, so we'll do that in just a second. But I am ready to answer these two questions. So that's what I mean by, other than finding the y's that go with our answers, this table answers all 4 of these. So for the intervals, I'm just reading right off the table I just completed. So intervals of increasing were -∞ to 0 and 0 to 3/2. Now I know it's tempting just to write -∞ to 3/2, but at 0 it really kind of levels off. It's not actually increasing. So it's actually less work just to blindly read off of your table that you've done and just leave them separate like that. Now, interval of decreasing ends up being 3/2 to infinity. So the last thing that I haven't quite finished is to do the max. I know that it happens when x is 3/2, and then remember that to find the y value, I go back to the original function. All right, so I'm plugging 3/2 into the original function, and when we do that, I think we get 27/16. So the ordered pair would be 3/2, 27/16. So I've got my critical values. I say that there are no minimums based on my table. I have the ordered pair for the maximum. I had to use the original function to find its y, and I have my intervals of increasing and decreasing. And so eventually we're going to put all that together to actually then hand sketch the graph on a grid that I will provide for you. In the homework, of course, it's multiple choice, but you should try sketching it by hand too, because it won't be multiple choice on the test. So right now, do hop on Desmos or some online graphing tool, and you can verify that, yeah, we don't have any mins and we have a maximum at this location, and that it increases on these intervals and decreases on the other interval. You can kind of verify that what we just did with calculus, without looking at a graph at all, really does match up with what you see in the graph. So I do want to show you one more example of a problem that you will see, and that is, again, you're just having to apply that same information. The fact that when the derivative is positive, the function is increasing, when the derivative is negative, the function is decreasing, and that maxes and mins happen at critical values. So this is where that original function where I was asking about increasing and decreasing, just to understand those concepts, I will not ask you something that easy again, okay? This, if you read the question, it states it multiple times. You are looking at the derivative, but you are asked about the original function. So you are not just going to look at this and say, oh, when is it increasing? 2.5-ish or 3-ish up to infinity. That's an Algebra 1, Algebra 2 question, okay? That is not a calculus question. This is derivative. I am asking you about the original. So, well, how do you know something about the original? You don't. You only have the derivative to go by. So we have to translate this to be something that we know. Now, the other thing I want to mention is that we're eventually going to talk about maxes and mins. Well, remember, maxes and mins, if they're going to occur at critical values. What are critical values? Critical values are places where the derivative equals 0, for one example. Well, this is the derivative function. When I say the derivative equals 0, it means its output is 0. So those are the places where the derivative equals 0. Circle them the second you get this problem. These should be the only numbers that you write anywhere on this problem. Do not be telling me the x's of the maxes and mins that are staring you in the face, because those are maxes and mins of the derivative, not of the original function that we're asked about. So back to A. I want to know when the function is increasing. I don't have the function. I have the derivative. So let's translate that to be something about the derivative. Well, the function is increasing when the derivative is positive. So that means the outputs of the derivative are positive. That means that I am literally trying to see when this function is above the axis, right? When its outputs are positive. So as I read left to right, I'm going to name intervals of x's here. This function starts being positive, the derivative starts being positive at -2, and it stays above the axis, it stays positive until 1. Then it starts again at 4 and goes on to infinity. And that's all there is to it. So we do have to be careful not just to blindly read off the graph and treat it like too easy of a problem, but it isn't difficult. So here, this is asking about when the original function is decreasing, but I don't have the original function, I have the derivative. So I need to translate it to a question about the derivative. And so I need to really see when the derivative is negative. So I chop the graph in half again. I want to know when the outputs of the derivative are negative. And as I read left to right, we start negative from -infinity until -2. And then we go above the axis, and then we're negative again from when x is 1 to when x is 4. So as I mentioned, the circled numbers are the only numbers that should show up in any of your answers. Now, there's some infinities and negative infinities, but no other numbers. Okay? So then we need to locate those maxes and mins. We have these intervals of increasing and decreasing. And so I highly recommend just drawing yourself a picture. I still do this, and it's for me, not even for you. So for a max, to draw that, I have to increase, then decrease. What does that mean in terms of the derivative? It's going from being positive, slopes are positive, to being negative, right? Slopes of tangent lines are negative. So I am looking for the x's. The circles are the only possible answers where the derivative changes from being positive to being negative as I read left to right. So as I go across my x's, I was negative, now I'm positive. Okay, so my derivative was positive and changes to being negative here at this x of 1. The outputs of the derivative were above the axis or positive, and they changed here at this critical value, this possible max or min, to being negative outputs after that. So we were trying to go from positive to negative, and that occurs at x equals 1. You won't be able to tell me the y value of this. We'll have to learn some more to do that, and that's why this will say specifically x values, that's all you're naming. Then we're trying to find minimums. To draw that shape, I had to decrease then increase. which with the relationships that we should know by heart by now, because I've said them so many times just in the last 20 minutes, means the derivative is going from negative to positive. So read left to right and try to name the x's when that happens. So my derivative is negative, and right here at x equals negative 2, it changes to being positive. And again, over here, my derivative is negative, and x equals 4 changes to being positive. As mentioned, the circled numbers should be the only numbers that you see here. So I do think whenever you see these problems, again, I will give it to you in this exact form on the test. There are no surprises. The homework question is slightly different, although not much, just to be in an online format. But you will see this, and when you recognize this, circle those numbers and remind yourself they should be the only numbers, and that all you're really doing is just having one more opportunity to show that you understand that relationship between the sign of the derivative and the increasing or decreasing of the original. You don't have a graphing calculator for me anyway, but even if you did, this is a conceptual way to see if you understand those, that you can't cheat by graphing some function. You have no idea what function this even is to figure out, where this happens. You have to understand those relationships that we starred on like the second page. So you'll also see some problems where you're told some information about the derivative and asked to sketch the graph yourself, and you can see an example of that on the last page of the notes as well. So in our next section, we are going to continue talking about how derivatives can help us understand what an original function is going to look like, and also eventually to find its maxes and mins as we would want to do in many applied problems.